Hey everybody, it's Ripley again. We're moving on to chapter 3 today, and we're going to talk about measures of center and measures of spread. I'm going to show you some mathematical formulas and some mathematical concepts, and these really are the brick and mortar of statistical analysis. Think of these as the properties of real numbers, or the trigonometric identities, the things that we're going to use over and over and over again. We're going to talk about them ad nauseum throughout this semester. Excuse me, I'm going to get a drink of water. I've generated a small list of numbers here. This is a data set conveniently sorted for our use from smallest to largest. Let's just say for, I don't know, for giggles, that I went around to 10 schools in a specific school district and I asked them what their annual budget was in hundreds of thousands. So this would be 4,500,000, which means that it'd be $450,000, $500,000, et cetera, et cetera. This would be 2 million. 2,900,000, 3,500,000, etc. And it looks like our most expensive school has a budget of $4 million a year. Okay, and I just went around to these schools. Now we got to be careful. If this represents all of the schools in the district, let's say that there are 10 schools in the district, let's call them high schools, then this would be the population for that district. However, it would be a sample for the state or for the United States, et cetera, et cetera. So you got to kind of get this feel for how squishy stats is. Remember, statistics, there are lies, there are damn lies, and then there are statistics. You can write these things sometimes to say what you want them to say. I'm going to assume that this is a sample for now, but I'll make the argument back and forth in terms of whether it's a sample or a population, okay? Because that's really going to matter down the road. All right, let's go ahead and talk about what the measures of center are that we're going to discuss today. The measures of center are the mean, which I'm sure you guys know what it is. It's also referred to as the arithmetic mean. Arithmetic, they're the same thing, mean. Or you'll sometimes hear this referred to as the average. Average, sorry about that. A little extra there. There's also the median. We'll discuss all of these, so don't panic if you don't know them. And we'll talk about the mode. Those are the main measures of center. There's also something called a mid-range, which we'll talk about. That's kind of the average of the highest and the lowest values. So let's go ahead and get started with the mean. I'm going to give you some formulas that are going to make you look real smart mathematically, and we're going to actually do it with this. I'll show you guys tomorrow how to do this on your calculator, how to input it, so you can play with it so that the calculator and or the computer does the heavy lifting for you. Much of everything that we're going to do in this class can be done on either the calculator or the computer. I want to go through the steps with you so that you see how it's done if you had to do it by hand. Plus, I'm evil, and this is the way that we had to do things by hand back when we had to write stuff out by hand. I'm ashamed to say that when I took probability and statistics in high school and college, that we had to do much of this by hand. Yes, I'm that old. Okay, so let's go ahead and talk about the mean. First thing we need is the notation. The mean for a sample, if we're talking about a sample here, the mean for a sample is referred to as X bar. If we're talking about a population, it's mu, okay? And this is referred to not as moo like a cow, but mu, and I just think of it like that, okay? Either way, if I'm looking at a sample or if I'm looking at a population, this is equal to the sum of the data values divided by the number in the set, okay? Now, careful. This little n represents a sample. This is a sample size. So you'll sometimes see this written out as the sum of x divided by big N, which is, in this guy, we're talking about the population. You see that how the notation can get a little squishy. So this is actually mu here, assuming that these represent all of the schools in our population. Okay? All right, so what I would do is, if I had to do this by hand, I would simply add 4.5. I'm going to assume that this is a sample initially. I would go 4.5 plus 5 plus ... plus 40, and I would divide by, I think I told you guys that there's a total of 10, and you end up with 19.5. All right, which represents, we know that this represents what, $1.95 million. That's the average. All right. Nothing to it. Excuse me. We've done it 1,000 times. Now, what if our information is in a frequency distribution? Remember how we had those frequencies? Bear with me, you guys, while I find a little piece of information here real quick. What if our information is in a frequency distribution? Sorry, guys, this takes a little bit. Well, it's actually not a whole lot more different. See, that didn't make any sense. The problem is, let's say that our information looked like this, okay? And all that we had was the midpoints and the frequencies, okay? I don't have the actual data. Remember, this data was spawned from this data over here. But let's say that I didn't have this data sitting in front of my head. All that I had was, let's say, this frequency distribution right here, or this in absence of the data. And I have to find a mean. Well, actually what we do is we apply the idea of mean twice. And I'll show you what I mean when I say that. Remember how these midpoints were generated by taking the middle values of these classes. Okay? Now, if all I'm presented is this piece right here, then I have no idea where the data lies around 118.5. I don't know if all of it is 118, 119, 118, 119, 118, 119, or if it's the spread of data like we had here between 113.5 and 123.5. All I have is this. So it's actually pretty simple to find the mean. All I do is I take X bar, I assume that all of these frequencies, and I know that this smells like a pretty big assumption, but statistically it works out really, really well. Instead of worrying about, oh goodness, Ripley, where did the values come from? I don't know where they live. I don't care. I simply assume that they are all 118.5. So in other words, these two data values are going to be 118.5. These three data values are all going to be 128.5. These five, all 138.5, et cetera, et cetera. So what it does is it makes our lives a lot easier. We just take the sum of the midpoints times the frequency and then divide them by n. So in this case, what you'd want to do if you had a frequency distribution like this, you're going to take the product. That's why these things are so useful. You're going to take the product of all of these, and then you add them up and you divide them by n. Okay? Nothing to it. Because think about it. What it would be is if we did, again, we're in absence of this. If we wanted to list our data per the frequency distribution, it would be 118.5, comma, 118.5, comma, 128.5, and this would be 3 times, so 128.5, and then another 128.5, and then et cetera, until we picked up all 28 of our data values. That's really what this says. It's the sum of this times this. This which would be what, 137 or 237? So this would be 237. If I can't do that in my head quickly. So 3 times 128.5, enter, that's going to give me 385. 385.5. 5 times 138.5 is 692.5. Check my mathematics. I have a tendency to do crazy things. 8 times 148.5, and that equals 1188. Whoops, 1188. And then 6 times 158.5 is going to be 951. And then 4 times 168.5, 168.5 is going to equal 674. And I'm running out of room here at the bottom. So when I add all these bad boys up, I get 41. Sorry about this, it's down here in the margin, but that's okay. 4128. So my mean is 4128, which was just the sum of all those, divided by 28. And this ends up being, I'm a handy dandy calculator, 147.42. Now, look at where that puts me. That puts me somewhere square in here, which is where it should be, right? I mean, we know by now by looking at distributions, if I look at my histogram, let's see if my histogram's over here, that puts me right in here somewhere, which you would expect your mean or your measure of center to be. All right, now I'm going to scroll back over here, and as we do that, I'm going to talk. The measure of center is supposed to be representative of the most data values. In other words, it grabs all of the data values at once. Now, or not, excuse me, not all at once. It grabs the most that you can grab at a time. All right, now it may not be representative of all. In fact, it can't be representative of all unless all of the data values were the same. In other words, this 19.5 million for, or, yeah, 1.95 million for this data set, it gets pretty close. I mean, it represents in here this little chunk right here. Now, there's an argument that can be made. I mean, let's look really, really closely here. Okay, it's really closest to these two data values. It's way away from this. It's like 1.2 million away from this. It's almost a million away from this. However, we sort of have this Faustian deal with the devil that says, okay, we understand that it's not going to be perfect, but we're going to let it be the center of the data so that we're reducing the differences between the data value and the mean. We're putting it in a place where we hope that it's the most representative of all the data. Like on the histogram that we just talked about, that was representative of a lot of the data. When you have individual data points like this, it gets a little crazy, especially when you've got this great spread of data. I mean, look at this. We start at 450,000. We go all the way up to 4 million. It's going to be really hard to find a measure of center that is representative of the majority of this data, unless all of these middle numbers right here were clustered around 1.95 or 19.5. Okay? Now, I want to show you something that happens here that's kind of crazy. Now, let's say for a minute that instead of having this 10 value data set, let's say that there's this crazy school in the district, okay? And I mean, it's nuts. It flies Bill Gates in twice a year. It's got, 5,000 kids. They've all got MacBooks and iPads. And I mean, they got all the bells and whistles. And let's say that their annual budget is $50 million. I know that seems a little silly, but it really could happen. So in terms of the data, that would be 500 100,000s, right? So we end up with $50 million. Now, the new mean, if I plug everything in, again, I'm going to show you how to do all this on your calculator. You can throw this data set in, you can add 500 to it to see what happens, et cetera, et cetera. But when it gets spit out, the new mean is 63.36. But remember, this equates to 6.3 million. Now, you may be going, Ripley, why don't you just write these things in terms of millions? I'm doing that for a reason. You're often given data or charts or graphs in these really strange units. So you got to kind of get used to setting your brain so that you can translate back and forth from hundreds of thousands to millions, et cetera, et cetera. All right? Now, watch the problem here. 63 million, whoops, didn't mean to cross it out. $63 million doesn't represent any of the data in this data set. I mean, look, the highest, if you exclude the 500 or the 50 million, the highest is $4 million. So 6.3 million, I think I said 63, I meant $6.3 million isn't representative of that at all. It's also not at all representative of the 50 million. It's not even close. So what we have is, what we refer to in the mathematical parlance or in the statistical parlance is we have an outlier. We have this crazy outlier number. And what this number is doing is it's pulling the mean to it. Remember, in absence of that guy right there, our mean was 19.5. You throw the $50 million school in and the mean gets drugged to it. It gets sucked over all the way over here to 6.3 million. All right, or 630. Whoops, yeah, 63.36. Okay, so the problem with the mean is, let me change the color of my pen. The problem with the mean is it's really susceptible to outliers. It gets slapped around. If I had a really low number here, let's say there was a free school that didn't cost anything, you just wander around the woods all day and everybody volunteers and everything's given to them, then that would drag the mean back towards zero. Excuse me. So we have this quote-unquote measure of center that doesn't really measure anything because none of the data is represented by that outlier, okay? Or excuse me, by that mean. Whereas over here, when we had the 19.5, at least these guys over here were sort of representative of it. The bigger the data set is, the more the mean will represent a true center of the data, okay? So what we do with this, in the case of a measure of center that we want to be more accurate if we have this outlier value, is we use the median. Okay, so the median really is the physical center of the data. Physical center of the data. All right, and I'm going to give you one more example with just some real small numbers to play with too, just to let you guys play with this just a little bit. Okay, so like I said, conveniently I have arranged the data from least to greatest, which makes it a lot more useful. Let me go ahead and erase all this gibberish over here. Get rid of that, get rid of that. Pardon me for just a second. And get rid of that. Ooh, look at that, good erasing. All right, now all that you have to do to find the median is line up. The best thing to do is to sort the data first from least to greatest, which has been done for you. The other thing is to write down what n is. In this case, I've got 10. All right. So then all I do is I march over 10 values, or excuse me, I march over 5 values since it's the physical center of the data. So I just go 1, 2, 3, 4, 5. Now, because we have an even number of data values, that implies that there should be, wherever the median is, there should be 5 data values below it and 5 data values above it. Well, that's nice, because I got myself 5 data values below and above where the median is. This right here is the median. Now, again, because I've got an even number, what I need to do is take the average of these two numbers, which is really easy to see that it's going to be 20. But again, I'll show you with a couple of different size data sets that sometimes there's a little bit more mathematics to it. Okay? Excuse me. So the median in this case, the median is 20. Now notice the difference between 20 and 63.36. All right? Notice the difference between 20 and 19.5. 19.5 and 20 are really, really close. Now, let's go ahead and figure out the median when I have this new data value. Now notice that n equals 11. So when I go to look for the median, watch what happens. I've got 11. I'm going to go ahead and erase this for just a second. Now, I can't go over 5.5 values, so what I do instead is I just round up to the 6th value. So I go 1, 2, 3, 4, 5. Half of 11 is 5.5, but there is no 5.5, so what I do is I just jump up to the next value, which in this case, this is my median. Again, it's 20. That's a really cool phenomenon. Notice, with or without this god-awful, nasty monstrosity of a budget, the median was still 20. The median is referred to as resistant to outliers. In other words, outliers don't pull the median, notice 20 to 20, versus 19.5 to 63.36. The way that an outlier can pull the mean. The median is a really, really powerful measure of center for that reason. All right, let me give you a couple of interesting data sets just for giggles. All right, let's create a data set we're going to call, let's say, 2, 4, 6, and 8. All right? Excuse me. If I wanted to figure out the median for this guy, now again, notice that n equals 4 because there are 4 data values in the sample. I would count over 2, but again, I've got an even number. So the median actually lives between the second and the third values because you want a value that splits the data perfectly in half. So in this case, the median is going to be 4 plus 6 divided by 2, which is 5. So the median, even though the median is not in the data set, it's 5. Okay? Nothing to it. However, if I added a 10 to this data set, now the median would fall exactly on 6. Because, let me go ahead and erase here, because 6 is the split between the bottom, these 2 data values and the top 2 data values. And even though it represents the data value, it's still, that's what we say the median is. Okay, so hopefully you see how a median works. Hopefully that was helpful. All right, cool, that's the median. Now let's go ahead and move on to the mode. crank over here. The mode is simply the data value that occurs most. Now, so I've been yelled at for this, but I believe it to be true. This is mostly, no pun intended, mostly, see most and much, mostly for qualitative data or categorical, so qual data. Now, let me show you why. I stumble back here if I want to do the mode on the data value that I created before. Now, in this case, if you look through the data, the data value that occurs the most is 20. Now, we just got lucky on this. We got kind of crazy lucky, and I'll create a sort of a crazy data value or excuse me, a data set where it doesn't work. In this case, wow, what happened there? In this case, the mode is 20 because it occurs twice, and all the other data values occur one time exactly. Now, let me show you what can happen. Let's say that instead of having this data set, I'm going to add 2 more data values to it. Let's get rid of this crazy outlier. That thing just made all hell break loose. Let's say, for example, that I added 2 more 5s. So instead of having 10, I have 12 data values. Now, I realize that that's going to change the median, and it's also going to change the mean, but we're not afraid of that. I'm just doing this to make a point. In this case, the mode, I'll write it down here since we got a little room. If I add these 2 extra 5 values right here, so it would be 4.5, 5, 5, 5, 6.5, 7, 7, or 7, 20, 20, etc., the mode would be 5. Now notice, again, while the mode is 5, there's no doubt about that. All these values way over here, really from 7 on, from 20 on, that doesn't really represent anything for us. It doesn't help us. Not like when we had the median of 20 and the mean of 19.5. That was far more representative of the physical center of the data and the average of the data. So what we do the mode for is, what we use the mode for is we use it for qualitative data. For example, let's say that I took a poll of the color of shirts in a classroom. Notice that's qualitative, not quantitative. And you had 5 blues, 7 grays, 8 whites, and of course 3 pinks, one of which I may be wearing. You never can tell. Well, it's very difficult to talk about this in terms of finding an average. I mean, what are you going to do if you want to look for X bar? Are you going to add up the wavelength of the colors? Let's see, a blue plus a gray is like a bruise, plus a white is a light bruise, plus a pink makes it a fuchsia or a mauve. Doesn't make any sense. Or brown, or God, I don't have any idea what that. You artists in the group would be able to tell me. So this is just it's not going to work. All right. So if I try to do the median, how does that work? Again, am I going to line it up by wavelength and find the physical middle of the data set? It's not that there's no order to it. This is an absolute nominal level of data. So there's no order to it. So I don't know if which is better than, in other words, opinions vary in terms of which color is better than others. So what we do is we grab the one that occurs the most, and this is referred to as the mode. Now, is our 8 white shirts representative of the pinks, the grays, and the blues? I guess from a scientific or an artistic, I forget which is which. White is the collection of all colors in science, and it's the collection of no colors in art. I don't know. I don't know. A little non sequitur there for you. But at least with qualitative data, we have something we can sort of grab onto. Now, referring to this as a measure of center, it's a little specious, but we have something that we can hold on to in qualitative data and say, okay, well, here's the mode. Here's the data value that occurs the most. Right? Those are the big daddies in measures of center. They are the ones that you're gonna see the most, and you'll really see the median and the mean the most. But every now and then you'll hear the mode get squirted out. So hopefully that was helpful. We'll play with a couple extra ones in the next little lesson, and then we'll be done with the first section in chapter 3. All right. All right, there's one last measure of center that we have to talk about, even though it's the most sort of clunky, elementary measure of center that you've ever seen. It's called the mid-range. Mid-range. And I'm going to go back to our data set over here just so you can get an appreciation for what's going on. God, I beat these things up in these presentations, don't I? The range of the data, the way to describe the range is simply to take the highest and subtract it from the lowest. And that's actually a measure of spread, which we'll discuss in the next little unit. However, what the mid-range is it's very, very simple. Like I said, you could teach your 6-year-old, I have a 7-year-old son, I could probably teach it to him. You take the lowest value, which I think was 4.5, and you take the highest value, which I believe was 40, and you divide it by 2. In other words, it's the average of the lowest and the highest. It doesn't really give us a whole lot of information. It just tells us where the center point is between the lowest and the highest, which, what would that be, 22.25? 2.25. Oddly enough, because of the way that the data distributes itself, it gets pretty close to both the mean and the median. Okay. Now, I want to give you one more piece of vocab just really quickly, and then I'll be done. You guys are probably tired of listening to me, but that is what it is. Let's look at distributions, for example, and see, we're not in complete absence of data. Let's see if we can try and decide where the mean, the median, and the mode would live given a certain distribution. All right. So let's keep it simple. Let's talk about one like this. So this is going to be basically a histogram, just a really smooth histogram. It's pretty simple to see. It's pretty easy to determine just by looking at the distribution where the mean, the median, and the mode are going to live. Well, the mode's the easiest because it's going to live at the highest value. So we know for sure that the mode's going to be there. The median, remember, the median splits the data in half. Because of the apparent badly drawn symmetry of our data, I'm going to have the mode here. I'm also going to have the median. All right, because it splits it in half. So 50% of the data lives over here and 50% of the data lives over here. And then if you think about how an average works, this little guy plus this little guy way out here, if I take the average of those, it's going to be here. If I take any point around this axis of symmetry and I add those up and divide by 2, I'm going to end up in the middle. And that's really an oversimplification of how to find the mean. Actually, I guess it'd be an overcomplication if we were to add them all up. Okay, so the mean, the median, and the mode, because of the symmetry of this, lives in the same place. All right, how about one of these guys? This, if I were to go... All right. Now what I have is what's referred to as bimodal. Bimodal means I have two maximum values, or excuse me, two maximum numbers or maximum frequencies of data values. It's called bimodal. If I had 3 humps, it'd be trimodal. That's referred to as a multimodal data set. All right. So I'd have a mode here, and I'd have a mode over here. However, my mean and my median would live right in the middle. So here's my mean, living here, and so would my median. Again, the arguments are easily made. The mean, it's just balanced right through the middle. Think of the mean as the balancing point of the distribution. It'd be the place that you'd have to stick your finger if you were gonna balance this figure, so to speak. The median splits, again, 0.5, 50% of the data is over here, 50% of the data is over there. Now let's get into something a little more interesting, just this last little topic before I let you go. What if you had this guy? You got something going like this. Woohoo, like that. All right, now it's easy to see where the mode is. It's the highest value, right, or the highest occurrence, so the mode is here. Now, what do we know that we're assuming that these values out here, somewhere out here we got ourselves some outliers. In other words, they don't really fit in with the other parts of the distribution. And hopefully we know that outlier, what they do is they pull the mean to them. So these values that don't have a very high frequency number are going to take the mean and pull it over to them. So the mean would live over here. But we also know that the median is resistant to outliers. It may get pulled, but it's not going to get pulled as far. So the median's going to live somewhere around here. I'm going to draw this in here. Median. And the easy way that I remember this is the median is the physical middle of the data value. It's also when you've got this non-symmetric distribution,
it is the physical middle of the measures of center. The mode is on one side, the mean is on the other, and the median splits the difference. This is called skewed data. Skewed. And in this case, because the skew, I believe in French, skew means right, or right, try that again. I believe in French, skew means tail. So what I have is a skew right data. Skew, when you see skew in a data set, your spidey sense better start tingling because some weird stuff's going to happen. Your measure of center is going to get crazy. Depending, your mean could be way out of whack because it could be getting dragged by these outliers to give you a value that's completely non-representative of what's really going on. An example of when my spidey sense tingles when I hear a statistic, especially in context of what we've been dealing with in our economy, it's the housing market. When you hear somebody give you an average value of an average home value in a community, let's say, well, that average is going to be way off because you're going to have, like, I mean, most communities have multi-million-dollar houses. Now, there may only be, I don't know, 15 or 20 of these, but these outliers right here are going to drag the mean, the average value of a house in that community way up. There aren't any houses that are worth $0. They usually get torn down and they aren't considered homes anymore. So what you'll typically hear as a statistics, as a measure of center of the housing market in a specific community, is a median value. If you don't hear a median value of home values in your community, hopefully at this point you're starting to get a little suspicious of the information. It might be a little bit apocryphal in terms of what they're trying to tell you. So anyway, a right skew looks like that. A left skew, hopefully you can sort of figure this out. A left skew badly drawn is going to look something like this. So you've got this skew over here. Right here would be considered the skew. Sorry about my lousy drawing. All right. Well, that's about it for the first section of Chapter 3. I hope you enjoyed it. Tomorrow in class, I'll be showing you a bunch of techniques with using your calculator to be able to figure out a lot of the heavy lifting with the computations of these formulas. Okay? Have a good day. We'll see you tomorrow.